Okay, so we're going to go straight into reactions of carbon compounds. And we were talking a little bit about reactions of alkanes last time. And we also did a little bit about the different. Okay, so we're going to go straight into sorry about that. We also spoke about the different types of reactions that alkanes can go through. And we're also going to review a little bit about where hydrocarbons come from. So the sources of hydrocarbons. So that's really what we're going to go into. Let us do some review before we do that. So we spoke about naming alkanes, and this is a continuous chain, and this one is a branch chain with a branch attached to it on your right hand side here. All right, and who can tell me the name of this compound? Who can tell me the name of this compound? What's the name of? Go ahead.
Pentane.
Pentane, very good. So if you notice, it has 1, 2, 3, 4, 5 carbons. And for 5 carbons, we have the prefix or the beginning of the name pent. And because it contains single bonds, it's an alkane. So it's called pentane. And what about this compound, the second one?
Butane.
Sorry?
Butane.
All right, but it's not just butane sources, all right? It has a branch that you have to name also. You have to include that branch in the name. So the first thing you do is you have to number the carbons, and you need to start from the end that will give the branch the lowest number. So you cannot start from this end because the branch would end up with number 3. So the best thing to do is start from this end. So we see 4 carbons. Now we have here a methyl group, and that methyl group is on carbon number 2. So we start with the number 2, a dash between it. So it's 2-methyl butane. And it's butane because it has 4 carbons in the longest chain. All right, everybody comfortable with that?
Yes, miss.
All right, and those are the answers, obviously. All right, let's look at this. This is a CXC question. Define structural isomerism. So they say but1-ene, 1-butene, and but2-ene are structural isomers of molecular formula C4H8. Define structural isomerism. How would you define structural isomerism?
The occurrence of 2 or more organic compounds that have the same molecular formula but different structural formulae.
Very good. Structural isomerism is the occurrence of 2 or more organic compounds with the same molecular formula but different structural formula. So that's the meaning of structural isomerism, right? So remember, they're asking about the phenomena. So you need to say the occurrence, right? And then it says to draw fully displayed structures of but1-ene and but2-ene. So how would we draw but1-ene and but2-ene? First of all, let's try but1-ene. How many carbons will it have? How many carbons would but1-ene have? It would have 4 carbons, right? Now, the 1, what does the 1 mean? What does the 1 tell us? What information does the 1 give us?
That a branch is there.
Well, you have to notice that this is not an alkane, it's an alkene. So the number is really giving us the position of the double bond. Is that clear? So if you notice, you're not seeing any methyl or dimethyl at the front of the word. So you know that there are no branches in this molecule. Really, the 1 is giving you the position of the double bond. So it's telling you that the double bond is between the first and the second carbon. So the double bond starts at the first carbon. That's what but1-ene is telling you. And then you're going to draw the H's. Now, remember, in order to determine and ensure that you don't draw too many bonds around carbon, you make sure that each carbon has 4 bonds. So this already has 2, so you draw 2 more. This already has 3, so they only need 1. This has 2, so you draw 2 more. And this has 1, so you draw 3 more. And you add H's accordingly. All right, how about but, so that's but1-ene. How about but2-ene? For but2-ene, same thing, you draw your 4 carbons. But this time, where will the double bond be situated? Where would the double bond be situated, class?
In between the second and the third C.
Very good, it's between the second and the third carbon, right? And then you add your hydrogen. Again, this has 1, so you add 3 more. This has 3 already, so you add 1 more. This also has 3, so you add 1 more. And this has 1, so you add 3 more. And you add your H's. And just to do a quick double check, the molecular formula is C4H8, as stated in the question. So you make sure you have your 4 carbons, make sure you have 8 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So you have your 8 carbons. Now, they're asking us to draw and name one other structural isomer of C4H8. So you need to draw another isomer. Now, maybe what is coming to your mind is you would say, okay, here the double bond is on the first carbon, and here it's on the second. So why not put it here? And that would be another isomer. Why would that be incorrect? Let me draw it up here. If I have 4 carbons, and I decide to put the double bond here, right? Why would this be an incorrect answer to this question here? Anybody say why it's wrong? Or who thinks it's right? Who thinks that I should draw, this would be a good structural isomer, a third structural isomer to but1-ene and but2-ene, C4H8. Anybody, why does anybody see that think that this is the correct answer? And why?
Well, seeing as how it is showing similar molecular formula but a different structure based on the position of the double bond.
All right, very good. So I'm happy that you said that. It is this and this have the same exact structural formula. The name of this compound is butanene. Why do I say that? Remember, you always start naming where the double bond is located. You start to number the carbon nearest to the double bond. So you would start numbering from this direction, 1, 2, 3, 4. So really, this molecule down here and this molecule here is just flipped. It's like if you have it looking like this and the double bond is right here and the double bond was right here, all we did down here is put the double bond here. That's the exact same molecule. That's the exact same thing. You just flipped it around. So it's the same molecule flipped around. The structural formula is not different. Are you with me?
Yes, miss.
So that is why this is wrong, because this and this is the same thing. This and this is the same thing, is the exact same thing. So that's why it's incorrect. So we're going to draw the actual, another structural isomer of C4H10. So what I would do, and the main thing is you would draw the alkene, and then you would draw it with a branch. So and then you draw a branch. That's a structural isomer. Ensure that you have your hydrogens. One, two, three, four, five, six, seven, eight. So C4H8. Can you tell me the name of this compound?
Name of what?
The name of this compound.
2-methyl. 2-methyl propene.
Very good. 2-methyl propene. All right, and that is an accurate structural isomer. So do not, the main thing that you need to understand is don't get fooled when they ask you to draw additional isomers. So I don't want anybody drawing this compound like this. And then they ask you to draw another isomer and you draw this. These two are the exact same thing. They are just flipped around. Do you see that? Do you see the similarity? It's like me, if you have a pen, right? And the pen cover, so this is your pen, and you have the pen cover onto your pen, right? And then I say, give me another pen. And you just take the same pen and You give me, but you give me with the cover this way. It's the same pen. Do you understand what I'm saying? The same compound. Hello?
Yes, miss.
All right. So that's what we mean. All right, so the next question says, state one physical property of C4H8. So what are some physical properties of alkenes? Well, for hydrocarbons in general, you can put several answers. One, you can, you know that most of them are gases. So you can say it's a gas. You can also say that they have low boiling points. That's another physical property. You can also say that they are less dense than air. That's another physical property. They're also volatile, meaning you can burn them. And they're also not soluble in water. They're really oily substances, right? So they are non-polar. So those are all physical properties. Clear? Gases, low boiling point. Could also say low melting point. All of these are physical properties. All right, now let's go into the sources of hydrocarbons. Now, naturally occurring hydrocarbons you get from deep in the Earth's surface. They exist in liquid form, and they call that liquid form crude oil or petroleum, as I was telling you before, or they exist in gaseous form, which they call natural gas. So this is an oil drill somewhere, and basically you use this, these drills to dig deep within the earth and extract the oil. So where does Jamaica get oil? Well, these are the world's top 5 oil producing countries: Saudi Arabia, Russia, America, United States of America, Iran, China, and Venezuela. And we used to mainly get our oil from Venezuela. So natural gas. Well, natural gas is a mixture of 4 alkanes: methane, ethane, propane, and butane. And methane is 80% of the natural gas. The majority of natural gas is methane, and the other 3 make up the 20%. Propane and butane is removed, and they sell that and give you, make you cook your food. And natural gases, ethane and methane, are used to mainly generate electricity. And you use them to also cook. Liquid natural gas and liquid petroleum gas is what they use to cook. And they use liquid natural gas also as petrol in Germany to fuel the cars. So let's look at petroleum. Petroleum is oily and is a mixture of many, many hydrocarbons. It contains as many as 70 or more carbon atoms in the molecule. So you can have like 70 carbons just bonded to each other, one after the other, huge, huge molecules. And you can separate it out into different components. And you use the method of fractional distillation to separate out these different hydrocarbons. So first thing is you have many impurities. So they extract those first and remove the impurities. And once they remove the impurities, then they heat the petroleum to about 400 degrees Celsius. Then the liquid is put into what they call a fractionating tower. And the fractionating tower looks like this. So basically you have the crude oil coming in through this pipe, and they are heating it here to about 400 degrees Celsius. And then it enters this fractionating column. And what happens very quickly is that molecules that have different numbers of carbons in them will start to go to the different fractions. And then you have the gases that are coming off at the top. So if you notice at the bottom fraction, this comes off if the molecule has more than 70 carbons inside. But then fuel oil has carbons from C20 to C70. You have lubricating oil that they use to make like shoe polish and floor polish and waxes. Those have 20 to 50 carbons in those molecules. Diesel has 14 to 20 carbons. You have kerosene, 10 to 16 carbons, gasoline, 5 to 10. Naphtha, which is used in making several chemicals, that has 5 to 9 carbons, and then you have 1 to 4 carbons being the gases which come off at the top of the column. So the most, the one with the lowest number of carbons are at the top, and they have the lower boiling point. And those at the bottom have very high boiling points. So the fraction which remains liquid at 400 degrees Celsius will sink to the bottom, and they tap it off, and they use it to make bitumen or asphalt. And the other vapors rise to the top of the tower, and they collect those gases. As you go up the tower, the temperature decreases. As you go up the tower, the temperature decreases. So I'm going to show you a video of the fractional distillation process, but I just want you to know, let me show you the video first.
In our other videos, we have learnt how fractional distillation is used to separate hydrocarbons. You will learn how fractional distillation separates crude oil into useful fractions. Crude oil is the term used to describe unprocessed oil. That is oil that has been taken directly out of the ground, either on land or under the sea. It is an exceptionally valuable resource. It provides us with a great number of hydrocarbons, some of which are useful as fuels, and others are used in the manufacture of many different chemicals and even plastics. However, in the raw form as crude oil, it can be a viscous, dark-coloured tar-like consistency, and the different fractions of hydrocarbons must be separated by fractional distillation for them to be useful. Before we understand how fractional distillation works, we should be clear that crude oil is a mixture of hydrocarbons with different chain lengths, some being short molecules and some being very long. Intermolecular forces act between molecules, and the longer the molecule, the greater the intermolecular force. As you can see here, the small molecules have weaker intermolecular forces, and so will require less energy to break them apart and turn them into a gas. They have a lower boiling point. The longer molecules have greater intermolecular forces. More energy is required. A higher temperature will be needed to evaporate these molecules. They have a higher boiling point. Now we understand how chain length is related to the boiling point of a molecule. Let us look at how this method works. As you can see, crude oil is heated up to a high temperature outside of the fractionating column. The hot crude oil, now mostly in vapour form, is pumped into the column. The column has a heat gradient and is very hot at the bottom, going cooler as we move up to the top. Even at the very bottom of the column, where the temperature is still high, some long chain molecules with high boiling points begin to condense back into a liquid. These are collected at the bottom of the column. The rest of the molecules start to rise up the column, making their way through bubble caps in each tray. The bubble caps slow down the rate of the rising vapour, and eventually the vapours get too cool, condense, and are collected as liquids in the trays. Small molecules have low boiling points, and so condense much higher in the column, where the temperature is cooler still. As you can see, hydrocarbons with similar boiling points are collected in the same tray, and this is why they are known as fractions. They are mixtures of hydrocarbons with similar boiling points. Each fraction has some important uses. Some examples of fractions are petrol, useful as a fuel for cars; naphtha, used in the manufacture of chemicals; kerosene as aircraft fuel; diesel oil, used as fuels for vans, cars and lorries; and bitumen, a mixture of large chain hydrocarbons used to lay roads. Now, at the end of this video, you should understand that crude oil is a mixture of important hydrocarbons, and that fractional distillation is the method used to separate crude oil into useful fractions with similar boiling point. You should understand that small chain molecules are collected at the top of the column since they have lower boiling points, and larger chain molecules are collected further down the column as these have higher boiling points.
All right, so I hope from that video that you understand what fractional distillation is all about. So the vapors of the larger hydrocarbons, they will come off at the lower part of the tower, and those with lower boiling points will rise and go to the top of the tower. The gases will not condense because their boiling points are way too low for the tower, and so they come off at the top of the tower, and we call that refinery gas, right? So the higher boiling points come off at the bottom, the lower boiling points come off at the top, and the gases that have too low boiling points, they come off as gases that we call refinery gas. So petrol is topped off from the top trays because petrol has low boiling points. And the same thing we call gasoline that we use in cars. Kerosene and diesel oil, they are topped off at the middle trays. And kerosene we use in aircraft, and diesel we use in certain types of engines and vehicles. And fuel oil, lubricating oil, and waxes are topped off at the bottom trays. So here's a table that shows the uses of the different fractions and the number of carbon atoms and their boiling point. So for refinery gas, I said it's below 25 degrees Celsius and you have 1 to 4 carbon atoms, and you use it for cooking, liquid petroleum gas, liquid natural gas, petrol, 5 to 10 carbon atoms, and the boiling point between 25 and 170, and you use that in cars, aircrafts, and some solvents. Diesel oil, 250 to 300 degrees Celsius, 14 to 20 carbon atoms, and you use it for diesel engines. And fuel oil, lubricating oil and waxes, 350 to 400 degrees Celsius, very high boiling point. And you see these are large molecules, 18 to 30 carbons. So you just have all these carbons just bonded with each other, just stringing along. and the fuel oil you use for ships and power stations and different heavy machinery. And finally, bitumen, which is above 400 degrees Celsius, that you use for road surfacing to make asphalt. So this is a picture of the different fractions and what they are used for and the number of carbon atoms that are in each, that come off at each fraction. Now let us talk about cracking. Now, when you have petroleum and you distill it, we have two main problems. First is that the fractions which contain the smaller hydrocarbons, example, the petrol, are in greater demand, right? You have more people that want to put gas in their cars than you have that want to fuel like a train or a jet or a ship, right? So you have more cars than those things. So they are in higher demand. So what happens, and a second problem is that the carbon to carbon single bonds that are present in petroleum from burning, it makes them unreactive. So they have to convert them into more reactive hydrocarbons, which have double bonds. So those are two main problems. So that is why we need cracking. So cracking is the breaking down of the larger hydrocarbons into smaller, more useful ones. So say, for example, you have hydrocarbons that have 70 carbons. You can break them down to have between 1 and 4 carbons, and you can sell this more. You want to sell more of that because that is in higher demand. You have more people that want to cook food than you have that want to fuel a ship. Everybody with me so far?
Yes, miss.
So what you have to do is you have to break down those larger hydrocarbons into smaller ones, and we call that cracking. Now you have two types of cracking: thermal cracking and catalytic cracking. Can anybody volunteer to tell me what they think thermal cracking is all about and what they think catalytic cracking is all about?
I guess thermal cracking is the use of heat to I guess pressurize the the carbon atoms to become smaller, I guess, or the carbon molecules to become smaller. And catalytic cracking is probably using some other like a substance to force a certain reaction to cause it to become compact, I guess.
Right. So yes, you have it mostly right. So thermal cracking is about heat, right? While catalytic cracking is about using a catalyst. So let us first look at thermal cracking. So in thermal cracking, temperatures of above 700 degrees Celsius and pressures up to 70 atmospheres, you use that to break down the larger alkanes into smaller ones. So you use these conditions, and this will cause the alkane molecule to vibrate strongly because it is under heat, strong heat and pressure, and that will cause it to break. So you have your large alkane, you have heat, you have pressure or catalyst, and you will get smaller alkane and an alkene, which is also useful. Now with catalytic cracking, you take the long chain alkane, you heat it to about 500 degrees Celsius. You have low pressure and you need the presence of a catalyst. The catalysts are a mixture of aluminum oxide and silicon dioxide, and we call this zeolites. We call this zeolites. And catalytic cracking is where we get our petrol today, right? So let's go over that. So in order to get more useful hydrocarbons, we break down the larger hydrocarbons into smaller ones, and we call that cracking. There are two types of cracking: thermal cracking and catalytic cracking. Thermal cracking, 700 degrees Celsius and 70 atmospheres of pressure, and that causes the long chain alkane to vibrate and break. Catalytic cracking, we use 500 degrees Celsius, low pressure, and a catalyst known as zeolites. This catalyst is made up of aluminum oxide and silicon dioxide. So, again, this is a picture of catalytic cracking. You have the large hydrocarbons. They are broken into smaller molecules using a heat and a catalyst, and goes in, you go to the catalytic cracker, and you get your small molecules, and then they still distill them out to separate them for use. All right, so let us look at oil in the Caribbean. Trinidad and Tobago is the leading producer of oil and natural gas in the Caribbean, because about 40% of the gross domestic product is the GDP, and a large percentage of their exports are from natural gas. And Jamaica produces, we don't really produce, yes, we distill our own. We have our own fractional distillation industry, and we have that at Petrojam. So let us discuss some of what we just spoke about. What are the two natural sources of the hydrocarbons? What are they? Where do hydrocarbons come from? Hello? Where do hydrocarbons come from, class?
Crude oil.
Right, very good. So crude oil, which we can also call petroleum, right? And the second is natural gas. Natural gas. So these are the two, right? The two sources of hydrocarbon, petroleum and natural gas. All right. List the main uses of three fractions obtained in the fractional distillation of petroleum. So 3 uses of the fractions. Tell me some fractions and 3 uses. I can tell you 1, petrol. Petrol is used to fuel cars. Tell me another use of another fraction.
I'm not sure about the name, but bitumen or whatever.
Bitumen, yes.
It's used in the roof tiling and also in making roads.
Yes, used for road work, right? Roads and roofing. Used for roads and roofing. Roads and roofing. And the third? A third use of a fraction.
Kerosene is used in aircrafts.
Very good. Kerosene, which is used for jet fuel, right? Did you know that before this? That is kerosene all they use to fly airplane? Yes.
No, miss.
It is kerosene all they use to fly airplane. However, the difference between the kerosene oil we put in our lamps and the one that they use to fly the airplane is that the kerosene oil in the airplane is very pure, free of any impurities or water. All right. So that is the difference. We get the, the mediocre stuff because it's just a lamp. But if they were to have like even just a small amount of water or any impurity in the kerosene used in the aircraft, you would have big problems in the air. All right. Okay. What is meant by cracking? What is meant by cracking? What is cracking?
The shortening of large alkane molecules to turn them into a shorter, more useful version.
Right, so very good. Cracking is the process by which you have a long chain hydrocarbon and it's broken down into shorter, more useful ones. So it's the process by which long chain hydrocarbons are broken down into shorter, more useful one. All right, what is the difference between thermal cracking and catalytic cracking? What's the difference between thermal cracking and catalytic cracking? Come on, quickly.
Miss, like thermal uses heat alone and catalytic cracking uses heat and a catalyst?
Yes, very good. So in thermal cracking, what temperature do you use and pressure?
700 Celsius, so temperature. And
You use 700 degrees Celsius and
70 ATM.
70 atmospheres for pressure, right? And in catalytic cracking, what is the name of the catalyst?
Aluminum oxide and silicon dioxide.
A mixture of aluminum oxide and silicon dioxide known as?
Zeolites.
Zeolites, right? A mixture of aluminum oxide and silicon dioxide known as zeolites. So that is what we have for the cracking. So what I am going to show you now is a video of how cracking is done.
In this video, you will learn about the process of cracking, how it is carried out, and why it is done. From our video on fractional distillation, you should know that crude oil is a mixture of hydrocarbons with different carbon chain lengths. Smaller hydrocarbons have a lower boiling point and are more volatile, making them easy to ignite and more useful as fuels. Larger hydrocarbons have a higher boiling point, are harder to ignite, therefore not as useful as fuels. We use a lot of fuels in our day-to-day lives, driving cars, aeroplanes, lorries, and even heating our homes. This means there is a very high demand for small chain hydrocarbons. However, after fractional distillation, we find that we have a large supply of long chain molecules. The process of cracking breaks down long chain alkanes into a smaller alkane and alkene molecule. This allows the supply of short chain hydrocarbons to meet the demand for them, as the longer chain alkanes are broken down into shorter alkanes and an alkene. The alkenes are also useful as these can be used in the manufacture of plastics. Here is an equation showing that C12H26 is broken down into octane and butene. There isn't a set way that these molecules are broken down. In fact, C12H26 could also be broken down into decane and ethene, or even butene, pentane and propene as these equations show. The large hydrocarbon is broken down in quite a random way. Just note that in each equation, of course, since we had 12 carbon atoms and 26 hydrogens going into the reaction, the same must come out. The process of cracking is carried out in one of two ways, either by thermal cracking using high temperature and pressure, or by catalytic cracking at low temperatures and pressures but using a catalyst. In thermal cracking, the large hydrocarbons are heated to temperatures up to 750 degrees C and a high pressure of 70 atmospheres. This high temperature and pressure breaks the bonds between carbon atoms to make smaller molecules. Catalytic cracking is the method used mostly in industry today. The large hydrocarbons are heated to around 500 degrees C and are passed over a zeolite catalyst. The catalysts chosen tend to break the bonds in the large hydrocarbons and make molecules of between 5 to 10 carbons in chain lengths, making them very useful in petrol. Now, at the end of this video tutorial, you should know that cracking is the process in which large alkanes are turned into smaller alkanes and an alkene molecule, and that there are two types of cracking: thermal cracking using high temperature and pressure, and catalytic cracking, which is the method preferred in industry as it uses lower temperature and pressure and produces more molecules that are useful in petrol.
All right, so I hope that from that video, it's cemented in your mind the difference between thermal and catalytic cracking. And as was said in the video, it is also very random how the cracking occurs, meaning that you can have any number of carbons. It's really random, any number of carbons in the alkane and any number of carbons in the alkene. It's just that the number in the products that you get must add up to the original number that you have. So let's look at this alkane, octane, CH818. If it were to undergo cracking, tell me some possible products. And what I will do is I will tell you one. Say we got pentane for one of the products. What would the other product be? The other product must be. How many carbons the other product must have?
3.
3. And how many hydrogens?
12. Not 12. Like 6.
It must have 6, right? And this is an alkene, so it's called propene, right? So as you can see, 5 and 3 is 8 and 12 and 6 is 18. So you get back what you started with. But octane can also produce, let's say if we produce butane as our alkane, what alkene must we get? What's the second product?
Butane.
Butene, very good. So we have C4 and how many H's?
6.
8, right? C4H8. Remember the general formula for alkenes, CnH2n. So if you have however many carbons you have, you just double the number for hydrogens. Let's do one last one. This time, sorry?
So in that case, the amount of hydrogens don't necessarily have to add up to the one in octane.
Oh, yes. How much is 12 plus 8? Sorry, it's C4H10.
Oh,
C4H10. So 10 plus 8 is 18. Yes, it must add up. It must. You can't, it's not magic. So whatever you start with, you must end with. So here we have propane. And we're going to have two alkenes. We're going to have propene. And tell me the last product.
ethene.
Ethene. Very good. Excellent. All right, so you get the picture. So octane here can be broken down into all of these products. And again, it's very random. All right. Any questions so far? Everybody still with me? Carrie, say Kayla, still there?
Yes, ma'am.
Go over one more time, please.
Go over which one, which part?
From octane, first one.
Octane. All right, so basically what we're showing you is that when you crack a molecule, when a molecule undergoes cracking, it breaks down into smaller, more useful ones. So this molecule octane broke down into pentane, and you usually get an alkane and you get an alkene. Two products or two kinds of products. So for this first example, and again, it's random. So for this first example, they got C5H12. So the second product must be C3H6. Why? Because if you already use 5 carbons here and it's 8 you start with, the other 3 must make the product, the other product. You understand?
Yes, miss.
In this second example here, you have butane coming off as one of the products. So the second product could be butene because you already used up 4 of the carbons. So the final 4 carbons must be in the other product. And here we have 3 products. We start with propane and propene. So we have 3 carbons here and 3 here. So that's 6 already. So the other 2 must be ethene. All right, so that's what we mean. You're just breaking them up into smaller, more useful ones. Is that clear?
Yes, miss.
You have to make sure that one of your products is an alkane and one is an alkene. So for the alkane, CnH2n plus 2. So that's why it's C5H12. 5 and 2, 5 times 2 is 10 plus 2 is 12. And then for the alkene, it's CnH2n. So you have the 3 and then it's double to make 6. So to make sure you get your H's right. And all of them must add up to the original number. So 12 plus 6 is 18. Jordan, you had a question? No? All right, let's do one more. Let's say we had pentane. We had pentane, C5H12. Tell me some products that you can get. Tell me 2 products that you can get from pentane. If you cracked from cracking. Tell me 2 products that you can get. Hello?
C3H8,
C3H8, all right, and what's that called?
propane,
Propane. And
C2H4, which would be ethene.
Ethene. Very good. Good. Can we get anything else? What about C4H? H10. That would be butane. And what would be the second product?
Methane.
Methane. All right. What about C2H6? That's ethane. What will be the second product?
Propene.
Propene, C3H6, right? So that's what I mean. Just break them down into smaller, more useful ones. Usually an alkane and an alkene. This is an exception. All right, now let us go and talk about alkanes real quick. We are gonna run through this because we already discussed it face to face, right? So again, the general formula is CnH2n plus 2, and it's saturated. What does saturated mean?
Only contains single bonds between the carbons.
Right, it contains single carbon to carbon bonds. And so they are usually unreactive, and they all end in ane, right? So alkanes that have 4 or more carbons show structural isomerism, meaning that they have the same molecular formula, different structural formula. So let's look at ethane. Ethane is one of the simplest alkanes, and it has covalent bonds, meaning they are sharing electrons. Now, the melting point and the boiling point of alkanes will increase as the size of the molecule increases. So the first 4 alkanes, methane, ethane, propane, and butane, have low melting and boiling points. But as you increase the number of carbons, they will have high melting and boiling points. So these first 4, they are gases because their melting points are so low and boiling points are so low. While alkanes that have 5 to 16 carbons, they are liquids because they have medium or midway melting points and boiling points. While even more carbons, 17 or more carbons, are solids because they have really high melting points. All right. That's where you get your waxes and those things. So as you know, the names methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane. And then as you go to 11, it's undecane, dodecane, tridecane, tetradecane, pentadecane. Now, remember we spoke about the types of reaction. So you now know that alkanes can go through 3 types of reactions. Combustion. What does combustion mean? You are burning it in oxygen, right? Substitution. What does substitution mean? What is taking place in a substitution reaction? In class, what is it? Go ahead.
The halogens are taking place of the hydrogen atoms.
Very good. So a halogen is substituting or taking the place of a hydrogen atom. And in cracking, what is cracking all about? What is cracking all about? Hello, we just learned cracking, you know? What is cracking all about?
When long hydrogen carbon hydrocarbon chains are broken down into shorter hydrocarbon molecules.
Very good, very good. And those are the 3 types of reactions that alkanes can go through. Excellent. So let's look at combustion again. Combustion is when you burn the hydrocarbon in oxygen, and this should be an arrow right here. So if you have methane, you react it with some oxygen, you will get water and carbon dioxide. And that is what we call complete combustion, because you have enough oxygen. Now, in the absence of enough oxygen, you will have incomplete combustion. And in that case, instead of getting carbon dioxide, you get carbon monoxide. And that is highly poisonous. That is highly poisonous. So if you notice, in some places in America, people die from carbon monoxide poisoning all the time. And they have to keep what is called a carbon monoxide detector in their houses. Why? Because there are sometimes when they have a heating system, and that heating system have methane gas, and it is burning to produce heat energy. And what happens if they don't have enough air? It produces carbon monoxide, and it can kill you in your sleep. So gas boilers that people have in their homes, you have to make sure it's being serviced, so that when it's burning all that fuel and producing the heat, you are not getting carbon monoxide coming off. So let's look at complete combustion. If you have enough oxygen, you get full carbon dioxide and water. So here we have C2H6, that's ethane with oxygen, carbon dioxide and water. So let's look at this one, butane, and we have oxygen. So we're going to get carbon dioxide and water. And let us balance this equation. Over here, how many carbons do you have? Hello?
8.
8. So what do I need to do over here?
Put 8.
Put a 8. Good. And then now, let's balance off our hydrogens. We have 2 times 10 is 20. So I need to put what here to get 20?
4.
I need to put a 10, right? 10
But
times
the-
2 is 20.
But the oxygen in the carbon dioxide.
All right, let's look at the number of oxygens. We have 16 here plus 10. That is going to give us 26. And here we have 13 times 2 is 26. Do you see that it's balanced?
Yes, miss.
All right. And there you have it. There you have it. All right. Now, this is the chlorination, or we can call this the substitution reaction, or another name for it is halogenation. All are correct. And what that means is you're taking out the hydrogen from the molecule, one hydrogen, and you're replacing it with a halogen. And in this case, it's chlorine. And so one of the hydrogen come off, and you get HCl and chloromethane. Then the second time you do it, you get dichloromethane, then trichloromethane, then tetrachloromethane. Right? And if you did the homework, I asked you to do it with bromine. So I hope you did. Now let's talk about the uses of alkanes. Alkanes are mainly used as fuels. So they burn easily as fuel, and they release a large amount of energy. So it's an exothermic reaction. and they are clean burning. So they burn with a clear blue flame, and they release, usually if it's complete combustion, you get water and carbon dioxide. And they're also stored easily as liquids in containers, and it makes it easy to transport. For solvents, you can use them to dissolve other non-polar solutes. So things that are oily, right? You can use it to dissolve. So naphtha is used as a solvent, and they usually use it if you ever smell like paint thinner and those things, they smell like gas. You ever smell paint thinner and it smell like gas? It's a hydrocarbon, right? You're using it to dissolve all of these oil paint chemicals that they are mixing up. All right, let's talk about biogas. Now, biogas is when you break down organic matter. So like fruits and vegetables and peelings that are spoiled, and you throw them out. It is a renewable energy source, and you can use it. It can come from organic matter. You can use manure, you can use farmyard animal waste, you can use food waste and organic waste from the food industry. So any old food that you throw out, animal waste, manure, things like that, you can use to produce biogas. So what you do is you take the organic waste and you put it in a sealed anaerobic digester. It's just a container that is sealed, free from air. And so if you see this word anaerobic, that means without oxygen. And so you have these anaerobic bacteria that are inside the organic waste material, and they digest the organic material in the absence of oxygen. So you have to have it in a sealed container, and then they produce biogas. What do they produce? This bacteria actually produces 60% methane and 40% carbon dioxide. They also produce other gases such as hydrogen sulfide. That is why when you smell that rotting container with all of that, it stinks because of this hydrogen sulfide gas. So you can use biomethane to fuel cars and to heat homes. And then the undigestible material that the bacteria did not break down, they can still go back and use it as fertilizer. So isn't that a great renewable energy source that people can use? Because every time you cut up one tomato, you have a piece like that you throw away. Not true? And you can use that to actually produce gas that you can then turn around and use it to put in your car and also fuel, even to cook with. So it's renewable. So this is how it works. Again, you have all these products, excrement from livestock, raw garbage, all of this organic matter. You put it in your sealed digester, and you have to keep it away from oxygen. And you have this bacteria that's inside, and it breaks down the organic material and it produces methane gas. And then you can use it to use it as fuel. So this is a very, very, very great way to produce energy. I'm going to show you a video to talk more about biogas. Wow, do you see that amazing cycle? It starts from the plate and it go right back to the plate. Right? So biogas is all about anaerobic digestion of these organic materials to produce methane gas, which is used to fuel cars and electricity. All right, the last thing we're going to talk about today are about alkenes. And alkenes are mainly used as fuels also. But the main difference between alkenes and alkanes is that they contain double bonds. They contain carbon to carbon double bonds. And we say they are unsaturated. Now, alkanes, their general formula is CnH2n. As I said before, just double up the number of carbons to get the number of hydrogens in alkenes. And we can do a quick exercise here for you to decide what would be the molecular formula. If you have 11 carbons, it would be C11H22, because you just double CnH2n, you just double up the number of carbons. So for C13, how many H's would you have?
Okay.
26.
26. And for C32, how many H's would you have? 64, right? And for C21, how many H's would you have? 42, right? So that's what we mean. When you follow the general formula, it's easy to determine how many H's and how many hydrogens you will have. All right, so that's that. So the simplest alkene is ethene. Tell me why methane does not exist.
Because carbons need at least 4 bonds.
That's true, but that's not why methane doesn't exist. Because if you had methane, there would be no other carbon to double bond with. So remember, the functional group of an alkene is the double bond. And for meth, the meth group is only one carbon, so there are no other double bond. There are no other carbons to form a double bond with, right? So methane does not exist. So for alkenes, the simplest one is ethene. And that is how it looks, right? 2 carbons and 4 hydrogens. That is a dot and cross structure where you have 2 shared pairs, right? Which means 4 electrons, 2 shared pairs, right? That's what gives you a double bond. Now let's talk about alkene reactions. Now alkenes undergo 2 types of reactions. The first is combustion, which you know already is just oxygen reacting with the hydrocarbon, and addition reaction. Now, what do you think the difference between addition and substitution would be? So for alkanes, they undergo substitution, but for alkenes, they undergo addition. What's the difference between those two? Anybody? What's the difference between substituting and then adding? Should I wait till 4 o'clock for you to tell me? Nobody knows? You don't know? Have no idea?
Not sure.
All right, so addition is exactly what it says. It's you adding another atom to the molecule. While substituting, you are taking out an atom and replacing it with something else. So in substitution reactions, like halogenation, for example, you take out a hydrogen and you replace it with a chlorine or a bromine or iodine. But in addition, you don't take out anything, you just add on something else to it. So we're going to talk about that. Let's look at, again, addition. Here, you have chlorine and you have the ethene, which is a double bond. And what happens is this double bond breaks and forms two single bonds. And the chlorine attaches itself to the single bonds here, as you can see, and you have dichloroethane. That's an addition reaction. The double bond breaks, and then whatever it's reacting with is added on to the alkane. So what is formed is called a haloalkane. Haloalkane. Halo from halogen and alkane because the double bond is gone. So again, we have bromine here. And again, the double bond is broken. You have two single bonds that attach to give you this haloalkane, which is bromoethane. Bromoethane. Now, you did this in a lab before. So if you have bromine, or some people call it bromine water, coming in contact with this alkene, what observation, what do you expect to see? What color change? So the bromine is originally red-brown. What do you expect to see?
Will change the colors.
Very good. The red-brown bromine will decolorize to colorless. So you will see a color change from red-brown to colorless. All right, and that is how we tell if something is an alkene. We react it with bromine, and if it changes from red-brown to colorless, we know that that substance was an alkene. Another reaction, addition reaction is called hydrogenation. What do you think? If halogenation is when you use a halogen, what is hydrogenation?
Using hydrogen, miss?
Using hydrogen, very good. So when you use hydrogen, you then react the alkene with hydrogen and it will most definitely produce an alkane. Now you must remember the conditions that are necessary. You need a nickel catalyst, you need 5 atmospheres of pressure, and you need 150 degrees Celsius. For the temperature, you need a nickel catalyst, 5 atmospheres of pressure, and 150 degrees Celsius of temperature. So here we have ethene. Again, the double bond will be broken and you get the single bond, and the hydrogen will just be added, right? And you get your ethane molecule. Again, you need a nickel catalyst. You need 5 atmospheres of pressure, 150 degrees Celsius, hydrogenation. All right, the next reaction, addition, is with hydrogen halides like HCl or HBr or HI, right? All of these are hydrogen halides. And again, it's the same principle. You have the double bond, it will break. And then you have the hydrogen going on one of the carbons and the halide going on the other one. So the HBr, they will go across the double bond and you get your this is a haloalkane as well, right? Bromopropane, 2-bromopropane, and it's 2 because the bromine is on the second carbon, and you can also get 1-bromopropane. All right. Suppose you are reacting it with HCl instead. What would be the products? Suppose you were reacting it with HCl instead. What would be the products? You would get 2-chloropropane, right? And what would be the next product? 1-chloropropane, right? Because a Cl would be here instead. Now, you can also add water to the alkene, and we call that hydration. So if you add hydrogen, it's called hydrogenation. And if you add water, it's called hydration. Now, when you add water, you will get a hydrogen atom, right? And you will also get an OH group coming off, and that will form an alcohol. So this is what it looks like. Now, the conditions: you need a catalyst. The catalyst is phosphoric acid. You need 60 to 70 atmospheres, and you need 300 degrees Celsius. So again, the double bond will break, and you have the H is going to attach, and the OH is going to attach. So you get ethanol, right? So if you start off with ethene, you're going to get ethanol. If you started off with, say, propene, you're going to get propanol. If you start off with butene, you're going to get butanol. All right. Again, you need 300 degrees Celsius, 60 to 70 atmospheres, and a catalyst, which is phosphoric acid. So that's actually how they make ethanol in industry. They take ethene and they put the pressure, the 300 degrees temperature, and the phosphoric acid catalyst, and then you get your ethanol. The unreacted gas that didn't turn to ethanol, they recycle it and put it under more pressure, put it at 300 degrees again with the catalyst, and you get ethanol. So that is how they prepare ethanol industrially. So in industry, the yield is very low. So they keep having to recycle the ethene and put it back into the container. So it comes through and you get some alcohol and some ethene, and you put it back in the reactor to get more ethanol and increase the yield. You can also react the alkene with acidified potassium manganate, and this is another way that you can tell if something is an alkene. So you use acidified potassium manganate and you will get a dialcohol, which means it has 2 OH groups instead of 1. And what will you see? Well, you will see the color change from purple to colorless. The potassium manganate will change from purple to colorless. Why? Because the alkene is acting as a reducing agent. So it reduces the manganate ion to the manganese ion. So here you have it. You have your ethene, and you react it with potassium manganate, and you get 2 OH groups coming off across the double bond. And it's called a diol, which is ethane 1,2-diol. What do you use alkenes for? You use them as starting materials to manufacture chemicals because they can undergo addition reactions. You can also use them to manufacture ethanol and antifreezes, which are dialcohols, and you use them to make plastics or polymers, which we'll talk about later on. Again, you have a test that you can use to tell the difference between an alkane and an alkene. You can add acidified potassium manganate, or you can add a solution of bromine water. And if you add acidified potassium manganate, if it's an alkane, it will remain purple. But if it's an alkene, it will change from purple to colorless. If it's with bromine water, if it's alkane, it will remain red-brown. But if it's an alkene, it will change from red-brown to colorless. All right, and all of those is because of the alkene's ability to undergo addition reaction. So the addition reactions we spoke about today, alkenes undergo combustion, which is burning, and they undergo addition reaction. So what can you add? You can add a halogen, and we call that halogenation. You can add hydrogen, and we call that hydrogenation. You can add a hydrogen halide, and we call that addition of hydrogen halides. You can add water, and we call that hydration, and that produces an alcohol. And you can add acidified potassium manganate, which produces a dialcohol, which we spoke about earlier. So these are some questions. What are the conditions under which the following reactions occur? Hydrogenation of ethene. So if you want to go through hydrogenation of ethene, what are the conditions? So I need you to tell me the temperature, the pressure, and the name of the catalyst. Do you remember? So for hydrogenation, what is the temperature? What would be the pressure and the name of the catalyst? Hello?
Not sure.
See it there on the slide. For hydrogenation, what's the temperature, what's the pressure, and what's the name of the catalyst? It's right here. What's the temperature, what's the pressure, and what's the name of the catalyst?
This is a nickel catalyst and the pressure is 5. This is what ATM stands for, miss.
It stands for atmosphere.
5 atmosphere and the temperature is 150 degrees Celsius.
Very good. And then the next question is, what are the conditions for hydration? So for hydration, remember you're adding water and you're going to get an alcohol, in this case ethanol. So what are the conditions for hydration? Temperature, pressure, and name of the catalyst.
300 degrees Celsius is the temperature, and the catalyst is phosphoric acid, and the pressure is 60 to 70 atmosphere.
Very good, very good. And you need to memorize those, right? Because sometimes they come up on the exam. So here it is. So for hydrogenation, again, we need a nickel catalyst, 5 atmospheres and 150 degrees Celsius. For hydration, which is addition of water, we need phosphoric acid, 70 atmospheres and 300 degrees Celsius. All right, let's look at these past paper questions right here. It says the fully displayed structures of 2 hydrocarbons A and B are shown below. See, they show it below. Write the names of the homologous series. So you have to write if it's an alkane, alkene, alcohol, carboxylic acid, or ester. So, which homologous series is A from?
Could it be propene?
No, it's not asking you for the name of the compound. It's asking you which homologous series it is from. So you would lose the marks if you write the name of the compound. It's asking you which group is it from.
Alkene?
From the homologous series of alkenes. Very good. All right, and then we have B. Which homologous series is B from?
Alkane. Alkane.
Alkene. So don't throw away marks by not answering what you're asked, okay?
Yes, ma'am.
All right, now they ask you, what is the general formula for each one? So A is an alkene. What's the general formula for alkenes?
N+2.
So it's going to be Cn. They all start with Cn, but how many H's are going to be there? Remember, for alkenes, the number of H's always double up.
Oh yes, ma'am.
So it's CnH2n, right? Cn, and then the number of H's is 2n, it doubles. All right, what is the general formula for alkanes?
That means CnH2n+2.
Very good, CnH2n plus 2. All right, also very easy, 2 marks. All right, it says both A and B react with chlorine, but under different conditions. You remember we talked about conditions?
Yes, ma'am.
So state one necessary condition for the reaction for B, but I want you to tell me all 3. So remember we just spoke about halogenation. So tell me the conditions for halogenation. When you add, so this is the alkane, right? So this is a substitution reaction. You remember we were talking about it last time, and we said no reaction can occur with an alkane if it is in the dark. You need something that is necessary for substitution reactions. Anybody remember what we wrote in the notes? You need UV light. You remember that? That's necessary. You need UV light. It's necessary for B to react, for an alkane to undergo substitution. Hello, you remember what we were talking about on, what day was that? Last week. Whichever day that was when we were at school. I wrote in the notes, it's necessary, you need UV light, all right? So that's one necessary condition. All right, it says, draw the fully displayed structure of the organic products for the reactions between A and B with chlorine. So what would you get if you react A with chlorine? So let me just draw, I'm gonna draw A, so this is A propene. I'm gonna draw it. And then we're going to talk about what happens when you react chlorine with propene. So tell me what is going to happen. What's going to happen?
With it with fire. I'm not sure.
So this is a double bond here, right? So what happens when you react the alkene with something? It's going to break the double bond. You remember that? And it's going to form the single bond across the double bond. And then it's going to attach the two chlorine atoms to each of the single bonds. Do you remember that? All right, so again, this is what it looks like. So we're going to draw the final product. So you have the double bond, so it's going to be broken, and you have a single bond here and a single bond here. You have all of your hydrogens, like normal. And then across the double bond, you will have the two chlorine atoms forming, right? So that's the first product. Then they ask you to draw it for this one, which is this is butane. So we have butane, 1, 2, 3, 4, and we have hydrogens all around. And this is going to undergo what we call a substitution reaction, right? This one is called addition reaction or halogenation. And over here is going to be substitution. So in substitution, what happens? What happens in substitution? What will happen, class? Remember, I asked you to draw this out for homework. One of the hydrogens is going to come out, and what will happen after that? Hello? What happens when one of the hydrogen come out?
Miss, one of the chlorine will replace the hydrogen, and then you would have plus hydrogen chloride.
Right. So you have your compound. And you have a hydrogen coming off and a chlorine taking its place. So that is it. And that would give you 4 marks. All right. Next. The fully displayed structures for the 2 hydrocarbons, compound A and B, are shown below. Again, they ask you to name the homologous series. Which homologous series is A from?
Alkane.
Very good. A is an alkane. And which homologous series is B from?
Alkenes.
Alkenes. Excellent. All right. Then they said to name each compound. What's the name of compound A? What's the name of compound A, class?
Would it be 2-methyl butane?
Very good. 2-methylbutane, right? So you number them, and the methyl group is on the second carbon, which is the lowest one, and the longest chain is butane. So it's 2-methylbutane. All right, let's name compound B.
Butene.
But what in?
Butene.
Very good, because the double bond is on the second carbon. So the name is but2-ene. All right, and I'm not gonna, you see how many times? I think I copied about 3 or 4 past papers with organic chemistry. And I think this question came 3 out of the 4 times. So quickly, just tell me what is structural isomerism.
The occurrence of two or more organic compounds that have the same molecular formula but different structural formula.
Very good. Easy, 2 marks. All right, so it says to draw the fully displayed structure of one structural isomer for each compound A and B. So you're going to draw an isomer for compound A. So this is A. What would an isomer for compound A look like? Now listen. If you take this methyl group and you put it on this carbon here, right? So you take this and you put it over here. So who can see that that is the same molecule? That is, I repeat, not a structural isomer. Because all you would do is just start numbering from this end and it would still be 2-methylbutane. Do you understand what I'm saying? Hello?
Yes,
So what you need to do is come up with a better and another isomer. And one that is very good is you would take this methyl group and you make it a branch too. So you put it right there, so, right? And that is a structural isomer. So it would be propane and you have 2 branches attached. So we're going to draw that. And you have your branch at the top as usual, and the branch that was here, you take it and put it on the second carbon. So you see that looks very different now. Then you add your H's. Remember, each carbon must have 4 bonds. What's the name of this compound? What's the name of this compound, class?
2,2-dimethylpropane.
Very good. 2,2-dimethylpropane. They didn't ask you to name it, but just for practice. All right, and let's draw a structural isomer for B. So this is B here. What would be a good isomer for B? You could take the double bond and put it here, right? And you see that that would be but1-ene instead of but2-ene. So that's what we're going to do. Just take the double bond, put it at the first one, and draw the rest. And remember, each carbon must have 4. So that's called but1-ene. Right, so that's 2 marks. Look again. What is structural isomerism? Another question, you know, I think it come like 3 years in a row. I hope it come this year. What is structural isomerism?
Okay, the occurrence of two or more organic compounds that have the same molecular formula but different structural formulae.
All right, so if we see this, if we see this question on the exam and you don't get it right, what am I do with you? You know what we're gonna do with you? Drink some water. All right, let's look at the second question, part B. Compound P is a hydrocarbon. What's the name of compound P? How many carbons are in this molecule?
5. It's 5. 1.
1, 2, 3, 4, 5. So it's going to name pent something, right? And where on which carbon is the double bond located?
Between the 1 and the 2.
Right. So what would be the name of the compound?
Hence 1 in.
Very good. I remember to put the dash between the number. Could also say 1 pentene. All right. This says to state one physical property. Now, physical property means you're going to talk about boiling point. You're going to talk about state of matter, like if it's a gas, if it's a liquid or a solid, you're going to talk about density. You can talk about solubility or volatility. So does it have high or low melting point?
Low.
Yeah, a low boiling and melting point. Because they are hydrocarbons, you know that they are not soluble in water. So you can say that, not soluble in water. Yeah. And then chemical property now. Remember, it's an alkene.
You talk about the bonds.
You should talk about how it reacts with, like, because it's an alkene, a very easy thing to talk about here would be how it reacts with bromine water and potassium manganate. So you can say it's unsaturated and decolorizes bromine water, right? Or you can say changes bromine water from red, brown to colorless. We talk about, yes, the bonding, how it reacts. That's what chemical properties are talking about, how it reacts. All right. Clear so far? Still with me?
Yes, miss.
All right, good. All right, now let's talk about the fully displayed structural formula of compound P, and then you're going to draw an isomer of compound P. So again, P is called pent-1-ene. So it has 5 carbons and it has a double bond on the first carbon. So then you're filling everything else with hydrogens. All right, what would an isomer of this one look like? Where would you can switch the place of the double bond, right? Where can you put the double bond? Hello?
Could you put it between the second carbon and the third carbon?
Right, definitely. So you can switch it, put it between the second and the third carbon. And so the only thing is just don't put it back, don't put it out here at the end, right? Because it's the same as this one. And then you fill in your hydrogens. So this is pent 2-ene. All right, and that will give you 4 marks. Yes, it's a CXC no hard, students. You just have to really just answer what they're asking. And that would be it. Now, something that I want to show you is here in Google Classroom, I'm going to share with you a Google form that I made with some multiple choice questions that you can practice. Then I'm gonna let you go. So here it is. I'm going to send you the link to it.
Miss, this PowerPoint is the same PowerPoint as the organic chemistry one?
No, it's new. I sent you this one just now. I sent it to you when I sent you the link to the class. Yes, there's a new one. All right, so this is a quiz on alkenes and alkanes, and there are some CXC multiple choice questions that you can try, and they already have the answers there. So when you do it, you can see your score right away. So let's answer some of them. In which of the following processes is fractional distillation not used? Refining of crude petroleum, separation of methanol from methanol water mixture, separation of chlorophyll in a leaf extract, separation of liquid air into nitrogen and oxygen. Which one is fractional distillation not used? The answer is separation of liquid air into nitrogen and oxygen. Why? Because this process does not include boiling off the mixture and collecting the mixtures at different temperatures. So that's why the answer is D. The separation of liquid air into nitrogen and oxygen is you actually don't use fractional distillation for that. All right, which of the following statements best describes a catalyst? It increases the activation energy of the reaction. It alters the quantity of the products formed. It is always unchanged physically at the end of the reaction, and it's always unchanged chemically at the end of the reaction. Which one best describes the catalyst? Now the answer here,
D?
yes, very good. The answer is D. Why? Because the catalyst actually lowers the activation energy and it never alters the products. And sometimes it can be changed physically, meaning you can start out with a solid and you end up with a liquid based on the temperature or something. But the catalyst does not take part in the reaction chemically. So it is unchanged chemically. So that's why the answer is D. All right, this one. Which of the following sources of energy is the most commonly used in the world today? Nuclear energy, fossil fuels, biogas, or gasohol? Which one do they get the most source of energy from today?
Not sure if it's either B or C.
All right, so the answer is B. right? Biogas is coming around, but you know, see people I use their old food to make gas for putting in the car. You use fossil fuels, right? Right now, that's why we have petrojam. And even if you look in Jamaica, we don't have no nuclear power plant, right? So the answer is B, fossil fuels. That's what we are currently using today, the whole world. Petroleum. All right, this one is from an old paper. Which of the following could produce carbon dioxide and carbon monoxide as pollutants? Geothermal energy, solar energy, fossil fuels, or biogas? Hello? What could the answer be?
Not sure, Miss. My Wi-Fi wasn't working when we were going through this part.
Okay, so the answer is fossil fuels and biogas, because we just spoke about it, right? So, for fossil fuels, you get carbon monoxide because you have incomplete combustion. And once you produce biogas, if you have incomplete combustion, you will get carbon monoxide coming off, right? So that's why the answer is 3 and 4, which is D. Geothermal energy and solar. Solar energy, don't burn any fuel. None of these burn fuel. But fossil fuels and biogas burn fuel. They burn, biogas is methane gas, so it burns fuel. So because of combustion, you can get carbon monoxide. That's why the answer is D. All right, which organic compound undergoes addition reaction? Remember, we talked about addition reaction now, you know. So which organic compound undergoes addition reaction? Ethanol, ethene, ethanoic acid, or ethane?
Ethene.
There is ethene, very good. Because alkenes undergo addition reaction. Tell me some of the addition reactions you can have. You can have halogenation, which is the addition of a halide. What else can you have? What else can you have? Halogenation, addition of a halide. What's the addition of water called? What's the addition of water called? It's called hydration. What's the addition of hydrogen called? Come on, class. What's the addition of hydrogen called? Hello, what's the addition? When you add hydrogen to an alkene, what do you call that process?
Is hydrogenation.
Hydrogenation, yes. Lord have mercy. All right, next one. The compound propene, which is here, reacts with bromine to produce what? A, B, C, or D?
B.
Sorry?
B.
D, all right. Now, what would probably be helpful for you, the answer is D. What would probably be helpful for you is if you drew it out. So if you draw it out, CH3 would be C and 3H is around it. And then it's bonded to C, H, Then you have a double bond and then a CH2. All right, so when you have bromine coming in, it's Br2, so you have two bromines. They're going to come across the double bond, one here and one there. So you're going to have CH3, then you're going to have CH here and a Br there, CH and a Br, then H, right? So you see that is this CH, then CHBr, then CHBr. Do you see it?
Yes, Miss.
So that's why the answer is D. So the best thing to do is draw it out when you're not sure. All right. Which of the following structures represents butene? Sure. Which one is butene? A, B, C, or D?
B.
B. Yes, that's the answer, B, right? Butene, you see, it's at the second carbon, double bond. So that's butene. This is but1ene, this is but1, this is propene, and this is two double bonds. It's actually a dialkene. All right. When a hydrocarbon molecule is cracked, which two similar molecules are produced? So when you have cracking, what do you get? When you have cracking, what two things do you get when you have cracking?
Alkane and alkene.
So what's the answer to this question?
A.
A, very good, 1 and 2, right? 1 and 2. All right. Compounds in a homologous series, A, exist in the same state, meaning solid, liquid, and gas, possess the same molecular formula, differ successively by a CH2 group, possess only carbon in straight chains. What's the answer? A, B, C, or D? What's the answer? No, but if you don't know, say you don't know, so we can move on because they are waiting. I don't know if you're not going to.
A.
All right, the answer is not A, because remember we spoke about when we talk about fractional distillation, some of the hydrocarbons exist as you go up, right? Some of them exist as solids, some exist as liquid, and some exist as gas, right? So they don't all exist in the same state. The lower the number of carbons, those are gases. Then as you go up to higher carbons, you get liquids. And if you have a lot of carbons, you will have solids. The answer is C. They differ successively by CH2 group. Let me show you what we mean. Methane, CH4. Ethane, CH6. What is the difference between this and this? You have to add CH2 to this, to methane, to get this. Let's look at propane, C3H8. What's the difference between this and this? You have to add CH2. Do you see that they differ by CH2? Do you see it? If you add a C to,
Yes,
if you add a C to CH2, you get CH3. And if you add 2 hydrogen, you get C3H8. So that's why the answer is C. All right, next one. I think this is the last couple. And then I will send it to you to do by yourself. Ethene reacts with hydrogen, chlorine, and hydrogen chloride. These are all examples of which type of reaction: addition, substitution, condensation, or polymerization.
addition.
Most definitely addition, right? A. All right. What is the major source of alkanes and alkenes? The major source, where they get it from?
Natural gas, miss?
Natural gas is only methane, ethane, propane, and butane. But all alkenes and alkanes come from petroleum, right? Petroleum. I don't know why I have natural gases. The answer is petroleum. All right. The functional group in carboxylic acids is what? What's a functional group in carboxylic acid?
B.
B, very good. All right, so the others are pretty easy. So please try them on your own. I'm going to send you the link in the group right now. Try them on your own and see if you can practice. Again, this PowerPoint that we did today, it's in the group, and I'm going to send you the link to the activity, the Google form activity. All right. Any questions about anything before we go? So let me tell you what we have left to do.